Today I'm going to show the operation of Nvidia's CUDA C++. CUDA stands for Compute Unified Device Architecture. So the language that's used here is modified C or C++. I mean an extended C or C++. It is extended because some global variables are appearing here, such as this one underscore global, and as well as this weird bracket operator here. Okay, so it is some sort of extended syntax of C. So this is a C or C++ program, except that it has been slightly modified to support the CUDA or to utilize the CUDA GPU. So this program, what this program is trying to do is to add an array of two floats and then added each element of these arrays and put it into a third array. So in this example, there are 50,000 elements of a float array here and filled with random values here. And then of course you can just for loop these elements of these arrays and add them and put the sum to the third array. But the intention of the NVIDIA's CUDA is to parallelize the operation. So since the addition of every cell in the array is independent, by that I mean you can add the first element without any dependency to the second element, since this operation is embarrassingly parallelizable. So it can benefit from the CUDA GPU. So the function that does the add is this function here. So you will notice that this function has parameter, the first array, the second array, and the third array, which contains the sum of every element of the first two array. And the num elements is the size of the arrays. However, in this function, you will notice that there's no for loop. It's just adding one array, one cell from the array. So the reason that it is only adding one cell from the array, which is happening here in line 53, is because the background CUDA architecture is the one that is calling this function in a parallel manner, and depending on the value of this global variable will be used to index into the array. And this vector add is invoked in a slightly different way, the CUDA way of invocation here. And the invocation is using this weird bracket, greater than and lesser than bracket. The first parameter is the number of blocks. The second parameter is the number of threads per block. So you have to spend a little bit of YouTube tutorial to understand this. So block basically is just a group of threads. So, and that the number of threads specified in that block is specified here. So you can call like 1000 blocks, and number of threads per block is 100. So the number of threads would be 1000 times 100. So that is the level of parallelization. So it will call this function vector add simultaneously that number of parallelization count. So if the result of the multiplication of these is 3000, for example, 30 times 10, this is just an example. So the vector add 3000 simultaneous call of the vector add is executed at one time. And each of those calls are adding, are doing the sum of every cell in the array. So that is how speed is achieved in the GPU CUDA way of programming. And the principle here is you can see the malloc, which is an allocation of the from the host side, the CPU in the Intel CPU that my PC here is running. And there's also another malloc here, which is allocating on the GPU side. So because there's hardware involved here, the GPU and the CPU. So this one, the CUDA malloc is doing the allocation on the GPU side, which is an independent hardware apart from the CPU. And you can also see that we transfer whatever is allocated in the CPU is transferred to the GPU using this CUDA mem copy. And there's a direction. The direction here is host to device, the host being the Intel x86, and the device is the GPU. So the randomized float that is generated here sequentially is transferred to the GPU using this function call. And once the two arrays have been transferred to the GPU by these two calls here, we now invoke the vector add kernel. A kernel is a term for a parallelizable function in CUDA. It's just a function, but it can be invoked in a parallel way using the syntax here. And then the result is stored in the CUDA memory. We still need to transfer it back to the CPU, to the host memory, using CUDA mem cpy again, but this time the direction is from GPU to host. And then once that is done, we can for loop all of the elements and verify that indeed the sum of the two arrays is correct. After that, we do the cleaning up, the freeing of the resources. We free whatever is allocated in the CUDA, and then we also free whatever is allocated in the Intel x86 CPU, and we return. Now, because this execution involves two hardware, the CPU and the GPU, we could not debug into this kernel function here. For example, if I press F5 and then I will press F5 and F5, you'll see that I have exited here. I have exited and I haven't reached the breakpoint here. Okay, this breakpoint is not hit. So to hit that breakpoint, the CUDA toolkit installation added a menu here, Insight, and then in this menu, there's actually a menu item to do the debugging. So instead of using the Visual Studio way of debugging, you have to use this plugin added in Visual Studio. So if I will click this, and then as usual, we'll be debugging. If I'll press F5, and then I will press F5, and here you will see that we have entered into the kernel function of the CUDA. And here we can see that the I is 0 here. And then, so we added the first array cell of the array now. And then if I press F5 again, and then we went into the second call of vector add, and then if we check the I, it's 9152. So here it might look sequential at the point of view of debugging, because we are debugging Visual Studio. It might look that it is sequential, but in reality, the execution of the vector add function, or the correct term is kernel, is happening in parallel. So, okay, so this is happening in parallel. So I press F5, F5, and then if I will stop the breakpoint here and press F5, and then we complete the execution and bring up of the resources. So that is all, guys, and This example code is downloaded from this repository in this GitHub repo, and I'm actually using the vector add example. And I'm using Visual Studio 2019 here, and then I downloaded a 3.5 gigabyte CUDA toolkit in the Nvidia website for Windows 10. So once you do that, yeah, your Visual Studio will have this insight menu here, or maybe in the extensions, either of this, but you will have this menu, and that's all you need to have to be able to debug the example in the GitHub, the code example in the GitHub.